University, South Korea. I'll be your moderator for the whole session today. This is my great pleasure as always. And let me introduce our brilliant and honorable prestigious speakers here. So we already have Professor Bahwa Zia and Professor Shan Yong-jang and then Professor Anja Boysen. And today we're going to have Professor Inkyu Park from KAIST. And next week you're going to have another prestigious speaker from One University of Technology, Professor Lee Kyang-mai. So please wait for us next week again. And today we are going to have an amazing presentation from Professor Inkyu Park from KAIST Korea. And then I'm going to introduce all of these amazing people of our from the who will be our panelists after the presentation. So Stella and Shuhei and Z and Faye, and I'm going to introduce them later again, one by one. And let me introduce Professor Inkyu Park from KAIST. This is my great honor to introduce him. And he's the expert, great expert in sensors. And this will be the great chance for us to share and then to listen to his talk about the sensor and artificial intelligence. And Professor Inkyu Park received his BS from KAIST and then a master's from UIUC in the United States and PhD from UC Berkeley, or in the mechanical engineering. And he has been with the Department of Mechanical Engineering at KAIST Korea since 2009, although he looks very young, and as a faculty member. And he is currently a full professor and KAIST endowed chair professor here. And he has published more than 180 journal articles, which has very great impact, and more than 50 patents in the area of MEMS and nanoengineering. And his publications have been cited more than 16,000 times already as of April 2024. So I don't know about the updated number this month, May. And he's got so numerous awards, so I cannot list them all, but you can refer to his biography. So Professor Inkyu Park, this is your stage, and welcome.
Thank you very much for great introduction, and I'll now share my screen. Can you see my screen?
Yes, very clearly.
Okay, so it's my great honor and pleasure to speak in front of the audience, and also great moderator and panels in today's session. I have always admired and respected the what the experts have been doing in iCANX event, and it's my great pleasure to take part in this event as a speaker today. Today I'll be briefly explaining and introducing what we have done in the area of the gas sensors for the development of the smart electronic node systems and environmental monitoring systems. And also, we could improve that such kind of system by aid of the artificial intelligence technology. So now let me start my talk. So before talking about my main topic, I'll be briefly talking about our laboratory. And our laboratory name is Mint Lab. In the past, our lab name was Micro and Nano Transducers Lab. It's got the same acronym, but this year I was trying to change the name of my lab, and ask my student, we can give up this great name, Mint. We can choose any other name, and ask them to change the name. But actually, they came up with quite a good name, which I'm very happy about. Is Machine Intelligence and Novel Sensor Technology Lab. It's got the same acronym, and this is kind of more trendy and also this aligns with our sort of identity of our laboratory. We do a lot of artificial intelligence, and also we develop the novel sensor and then try to combine those technology together. So this is our new lab name, but with the same acronym, Mint Lab. And my student, actually, we have about 20 students, and about 20% of our students are international students. So if I think many students could be listening to my talk, and if you're interested in joining our lab as graduate students or postdoc, you're very welcome. And we have a very good, friendly, and also international uh, atmosphere for uh, research and also study. And many of our alumni are working as professors at the university, research scientists at the national institutes, and global companies like Samsung, Intel, and Siemens. And a few students are working as a postdoc researcher at other foreign institutions. Our main research directions are these fundamental technologies based on mechanical engineering, based design, nanotechnology, and also AI. We use AI to design and develop the nanostructures or sensors, but also we use the AI to analyze the sensor data. And we want to apply that to the smart sensors, especially in the area of the healthcare, robotics, environment, and metaverse. And I'll go through a couple of examples of what we have been doing. The first theme of our laboratory research is the ultra low power and integrated environmental sensor, which will be the main topic of today's talk. Uh, for example, we developed the monolithic sensor platform that's got the integration of micro LED for the activation of the metal oxide based gas sensor. And also we've got the gas sensor right directly on top of the micro LED platform to develop the ultra low power gas sensor. We also develop a lot of very low power micro heater platform, and on a single chip we can make uh, array of four different types of gas sensors, such as the thermal conductivity, catalytic gas sensor, and also semiconductor metal oxide gas sensors. And we can use the response from multiple sensor range. We also develop neuromorphic sensor, which mimics the function of the animal olfactory systems. So more detail will be explained later. The second area of our research is the wearable and flexible sensor for the human-machine interface and metaverse. For example, we developed the mechanical metamaterial, which deforms as mechanically as we design in the mechanical simulation. Then, as we apply some physical stimuli such as pressure or strain, then this mechanical metamaterial deforms. Then it will change the optical property, and by using the optical property change, we can use it for the self-powered physical sensors like strain sensors for the motion detection. And also we mimic some three-dimensional structure of the animal. For example, this is the beetle. Uh, on the shell of the beetle, we can observe this three-dimensional plate structure with some slanted angle, and we could use this structure to develop uh, highly sensitive and linear pressure sensor. And also we use some other biomimetic structures for the self-powered solar energy-powered pressure sensors and motion sensors. We also developed three-dimensional electronics, which is made of stretchable materials and also conformal to any kinds of three-dimensional shape. So it could be useful for the wearable electronics and a lot of healthcare applications too. And the third area also is about the sensor, but mainly on the biomedical applications. This one is actually a flexible electrochemical sensor array that can detect electrical impedance, concentration of the glucose and lactate, and also pH of the tissue when the medical clinicians uh, try to collect some sample during the biopsy process. They like to approach the proper location of the suspicious lesion, but we can use a computed tomography to do the proper targeting of the target tissue, but that actually is not able to obtain very important data collection, such as the characteristics of the tissue for the collection of the biopsy process. So we can use this additional array of sensors at the tip of the biopsy needle to collect some additional data so that the doctors actually can have more accurate sampling of the tissue for the biopsy. And we use similar platform for the flexible sensor, but instead of using the electrochemical sensor array, we use a pressure and temperature sensor, and also that is integrated on the radio frequency ablation needle. The radio frequency ablation procedure is actually one way to treat the cancer by concentrating the RF energy at the tip of the needle. We can sort of burn the tumor tissue by increasing the temperature. Then proper pressure and temperature control is quite important. And then we developed this sensor and we collaborated with the Samsung Medical Center in Seoul, and then we could commercialize this sensor on the RF ablation needle. And also, we are very interested in the wearable sensor that is not run by the battery, but that is run by the uh, wireless power transfer. And this is the wireless and battery-free sensor platform where the energy is transmitted by the magnetic field from the primary antenna underneath the mattress, and then this sensor attached on the skin of the patient actually gets the energy and operates the pressure, temperature, humidity, pH, color change information from the skin. So that this is useful for the patient who's got some problem from the stroke or uh, spinal cord injury, who might be in the danger of the pressure injury, which is quite critical for a lot of patients. And also, we develop similar platform for the wheelchair systems too. And lastly, to develop these sensors, we'd like to make more sensitive, robust, and also quite uh, mm, quite stable at the same time, quite linear responding structures. And to satisfy such kind of specification, we have to have very good surface engineering or this micro and nano structuring. So we develop various micro nano structures using hierarchical structures or three-dimensional nanofabrication methods, and also try to make some rough three-dimensional structures for high sensitivity pressure sensors. Also, we develop various transfer process on the fabric so that we can make some smart fabric devices too. So those are some very brief introduction about what we are doing in our laboratory. But the main topic of my talk today is the low power and sub-powered gas sensors. And this is a brief outline of my talk. I'll talk about the background, why we need this uh, research about the low power and sub-powered gas sensors. Then I move on to the main part of the talk, low power and sub-powered gas sensors developed by our group. And I'll talk about the smart environmental monitoring where we actually apply our developed sensor for the real commercial and industrial applications by collaboration with some Korean companies. Then I'll finish my talk with a brief conclusion. As all of you know, the importance of the air quality is uh, increasing and rapidly increasing. And because of that, the gas sensing is very important. And gas sensor has a lot of conventional applications. For example, in some disaster or some accident, we should have chemical leakage monitoring to prevent some toxic toxic substance exposure to the human uh, users or people living in the uh, domestic buildings or industrial sites. So this chemical leakage monitoring is very important. And also in the factory, the facility safety management. And in the public outdoor spaces, like in the highway, the air pollutant monitoring is also quite important. And nowadays, the importance of gas monitoring is expanding into new areas, such as the indoor air quality monitoring. And also by analyzing the breath gas, we can diagnose the status of the disease. For example, the lung cancer patients, they may have different concentration of the VOCs or nitrogen dioxide and other gas species. So by analyzing the components of the gases in the breath gas, we can sort of screen the disease in the early phase. We can also use the gas sensors for the growth monitoring or environmental monitoring in the smart farm. We can do the inspection of the products or quality monitoring in the very critical high-tech manufacturing facilities like semiconductor factories. And also we can do the healthcare monitoring by measuring some VOCs or other gases from the sweat or breathing. We can also do the analysis of the health status. So because of this expanding applications of the gas sensor, there is a quite rapid growing market of the gas sensor area. So in the conventional industrial sites or factory, you can see many gas sensors already installed to monitor any kind of possible leakage of like explosive or flammable or toxic gases. And typically, the gas sensor are quite big. They are bulky, and also because they're quite expensive, they're installed in limited places. But if you look at the future of gas sensor, we are talking about more compact or personalized and portable gas monitoring systems, such as the smartphones or small gas sensor node in the IoT systems. So for this to be realized, we should have a small and ubiquitous gas sensors. And to make it possible, these are the key requirements to be satisfied. Of course, the uh, very common mm, key factors for the gas sensor should be met. And also the power consumption, miniaturization, and also cost would be a big issue, right? And if you look at various types of gas sensors, such as electrochemical, optical, and catalytic combustion gas sensors, they are typically quite bulky and also expensive. Per each gas sensor, we are talking about, at least 100 to several hundreds of US dollars. And compared to these type of sensor, semiconductor metal oxide sensor, which is made of metal oxide, such as a transition metal oxide, including zinc oxide, indium oxide, tungsten oxide, tin oxide, titanium oxide, and etc. And then we use the change of electrical resistance of those metal oxide. Then that will give us the information about the gas concentration. So it's got a lot of promising factors, such as it's got high sensitivity. Also, the response speed is quite fast. Compared to other sensors, we can mass manufacture them, so low cost is a big advantage. And also, it's got small size, but it's got also some drawback, which I'll be talking about later. Let me briefly explain about the principle of the gas sensor made of semiconductor metal oxide. We use a metal oxide, then their electric properties are semiconducting. And for example, I'll give you explanation about the N-type semiconductor, such as tin oxide or zinc oxide. So in the N-type, the free electrons are charge carrier, right? So if we want to flow the current through the semiconductor, electrons should uh, easily flow. But in the fresh air environment, the oxygen molecule in the air, they get attached on the surface of the N-type semiconductor. And by grabbing one electron from the N-type semiconductor, they form these negatively charged oxygen ions on the surface. So these electrons, which are captured by the oxygen, they actually cannot be used for the charge transfer. So at the very surface shell, they will form the depletion layer of the free electrons. They form some energy barrier which inhibit the flow of free electrons. So because of that, in the fresh uh, oxygen environment, it has high electrical resistance because it has some depletion layer. Also, it's got high energy barrier because of the oxygen taking the free electrons from the N-type semiconductor. But when the reducing gases such as hydrogen or ammonia comes, the hydrogen or ammonia, they react with the surface adhered negatively charged oxygen ion. Then this will be detached by forming the water vapor, and then it will return the free electron back to the N-type semiconductor. So by doing so, it reduces the depletion layer and also it reduces the energy barrier for the electron flow. So in the reducing a gas environment, it will have lower electrical resistance. So we measure the change of electrical resistance to detect the gases. So that's the very simple explanation about how these semiconductor metal oxide gas sensors operate. And P-type semiconductor, they use the opposite direction of the electrical resistance change. However, one of the uh, drawback I would say is uh, it requires some kind of energy for the activation, which means in the room temperature or low energy condition, this reaction is quite slow and also not quite reactive. So we need some kind of energy to activate them by applying some heat. We're talking about the temperature above 200 or 300, even 400 degrees Celsius. Quite high temperature is needed to heat these semiconductor metal oxide materials. Also, we can activate this by shining light, which I will talk about later. So, for the last couple of decades, heating the semiconductor metal oxide was the major direction of semiconductor metal oxide gas sensor. And in the past, before 1980s, people used to use this bulk size heater, and they could easily consume the energy to just for heating the sensor larger than 1 watt level, several watt. But after 1980s, people, especially a lot of pioneering research and development was done in uh, research group in Kyushu University in Japan, and also a lot of spin-off companies like Figaro. They have developed a much lower power and compact semiconductor metal oxide gas as a platform. However, they will still consuming larger than 100 milliwatt, which is still quite large if you want to apply that to the mobile and IoT applications. After 2000, people have now applied the MEMS fabrication approach to make the heating platform much smaller so that power consumption nowadays in the MEMS commercial gas sensor, especially this one from the Bosch Corporation, they consume the power range of 20 milliwatt. So miniaturization of heater size has been quite um, important for lowering down the power consumption. With that background, in our laboratory, we have developed various technology to lower down the power consumption, lower than even 20 milliwatt. We're talking about milliwatt level or sub-milliwatt level to make ultra low power consumption gas sensor platform. I'll be briefly talking about what we have done in the past about 10 years. So first one, low power in the range of 1 to 10 milliwatt per sensor. Among many materials for the gas sensor, semiconductor metal oxide gas sensor, one-dimensional nanomaterials such as the nanowires or nanofibers have been very useful because they have large surface area to volume ratio, high chemical reactivity, and high uh, response speed. However, the biggest problem of one-dimensional nanomaterials for the gas sensor device was the integration of these materials on the device platform. Usually, the chemical synthesis is used for the fabrication of these nanomaterials, but they have to be somehow collected or harvested from the substrate, then deposited or printed on the electrode for the device fabrication. However, they're quite difficult to integrate as a manufacturable device in a repeatable and also mm, high throughput manner. So because of that, a lot of people have you developed how the techniques to uh, directly integrate or align these one-dimensional nanostructures on the device platform using laser-induced local synthesis of metal oxide nanomaterials, transfer printing using microstamp, inkjet assisted nanotransfer, or capillary assisted dielectrophoresis to align these pre-synthesized one-dimensional nanostructures on the device platform. In our laboratory, about 10 years ago, we developed some technique called direct and local hydrothermal synthesis in the hydrothermal um, precursor environment. So this figure actually is a cover figure from the advanced material, which was published about 9 years ago. You can see here, as we make some electronic device, we can design such that if we apply electric potential across these two points, they will be locally heated to generate the Joule heating. And this Joule heating will generate the heat transfer, convective heat transfer, and also because of the convective heat transfer, mass transfer also is accompanied inside the liquid precursor environment. So this little circle thing symbolizes the fresh precursors that are supplied continuously by the convective mass transfer. So this convection and also diffusion governs the transport of the precursor to this local hot zone. And this local hot zone, we use the endothermic reaction. High temperature will generate a higher chemical reaction. So according to the Arrhenius equation, at the high temperature, we've got high chemical reaction rate. So these precursors actually they react and form these nanostructures on the local hotspot. So using this process, we can do a direct synthesis and also simultaneously we can integrate these nanostructures directly on the electrodes for the sensors. In this platform, you can see it's got double layer. At the bottom, got some serpentine heater, and between the sensor electrode and the heater electrode, we've got some insulation layer. And heater is when heater is operated, then it does the same thing like this uh, transport of the precursor. And then at the local hotspot, these kind of nanostructures are synthesized. Then they make the interconnection between this interdigitated electrode array. And then after this synthesis, we can use the same heater structure not only for the synthesis, but also for the actual operation for the gas sensor. Because for the gas sensor operation of this metal oxide, we need a high temperature. I use this heater, which was originally used for the synthesis, also for heating the sensor for actual gas sensor operation. So we can obtain this some gas sensor signals from this platform. And I want to point out that by minimizing this gas sensor area in a very tiny region, we're talking about several tens of micrometer by about several tens of micrometer, we can make this sensor area very tiny so that we minimize the uh, energy for heating of this sensor materials. That's the main point of making this localized synthesis to realize low power gas sensors. And we could also make this synthesis in not only in this steady state and stationary precursor platform, but also we could use this microfluidic platform. So we could supply different precursors at the same time. If you know the microfluidics, inside the microfluidic channel, the Reynolds number is very small, so they're regarded as a laminar flow. So the liquid actually do not mix with each other. So we can supply different precursors without mixing them quite parallelly. So using this parallel supply of precursors, we can make different matter different nano materials at the same time. So this is the titanium oxide, copper oxide, or zinc oxide. We can also convert their surface with additional coating with the metallic nanoparticle precursors too. So after making this, so this is image of one device. From here to here is like only about 400 micrometer across that we have. It's integrated sensors made of different one-dimensional nanomaterials. So we can collect the signal from multiple sensors, and when some gas is given, we can use their uh, response to analyze which gas it is. So this was actually published in 2015. At that time, we didn't have much idea about machine learning or deep learning at that time. So we could actually use some very conventional techniques such as PCA or etc. to do the analysis. But after that, we actually started to apply the deep learning, which I'll be talking about later. So here we also developed this suspended microheater platform, and by applying the local synthesis through the electrochemical deposition, we can deposit the catalytic combustion catalyst for the catalytic combustion sensor. I use the local hydrothermal synthesis for the synthesis of P-type and N-type nanomaterials. And then this at the very left bottom corner, we just leave as a you know intrinsic heater. So when some gas is given, we use absolutely four different sensors. The first one, we measure the thermal conductivity. This one we use for the catalytic combustion property of gas. And the p-type gives uh, the resistance change, and n-type gives the opposite direction of change. So we call this as an orthogonal array of gas sensors because they use a completely different responses, which is beneficial for the analysis in the machine learning. So this is a fabricated device that when some gas is given, then we can collect the sensor signal, which shows quite different modality, and then they are analyzed by the deep learning method. So what we do here is we observe the transient response of the gas sensors. So for each type of gas sensor, we look at how the time-lapse image of the response changes, and we train them using the convolutional neural network method and the so-called CNN method. And this CNN actually can be very useful for the training of this sensor response image. And after training them, we could actually provide some unknown gas, and this trained data provides a quite good estimation of gas in terms of their classification, which type of gas it is, and also real-time estimation of their concentrations. We can apply this technology to do some very simple metaverse applications. So here we use a four target scent from banana, rose, and lemon. And then what we can do is we provide this smell of banana, rose, and lemon, and we can train their smells by this sensor array. And then also using the CNN method, we can have a training of different smells. And in one site, we give this smell of different, fruit or flower. Then they are, okay, let me stop this video for a while. So we can train this data, and then when some unknown gas is given, this machine learning actually can identify what type of flavor is, and then on the remote side, uh, the another human actually can feel the scent by this kind of very crude scent display devices. So when the rose is detected, then it is also displayed in the remote places. So this is a very crude uh, sort of olfactory display system in the metaverse applications. And we also developed the artificial olfactory neurons and neuron by the neuromorphic node system. Most of the electronic node system actually uses the approach shown here. We first collect the data from the gas sensor, then we convert data into digital form by the ADC, and they are stored in the memory and they are processed, and then we can do the gas identification. This is actually quite energy consuming process. But what the actual animal does is when some order is given, olfactory receptor, they will generate some spike-like signals. Then this spike signal actually transmitted through the neural system, and then they're analyzed by the brain, which is actually quite energy efficient and easier to analyze a signal. So we try to mimic this uh, function by developing some internal spike generating device. So we combine our semiconductor gas, metal oxide gas sensor with the transistor device called the 1T neuron device. So depending on the resistance change, the current will be changed, and depending on the current flow, this device generates the pulse with different frequency. So by analyzing the change of frequency, as you can see here, we can identify what type of gas it is and also what is their concentration. So here we use two different the neuromorphic sensor made of tin oxide and tungsten oxide combined with the 1T neuron device. Then when some gas is given, they will generate different pulse signals, and then they are trained by the neural network called the spike neural network. And then this will enable us to identify the type of gas and also their concentrations too. And we actually wanted to have some more interesting demonstration instead of just simple, nitrogen dioxide or carbon monoxide or ammonia. So I propose this experiment to my students. Why don't we, demonstrate with more appealing applications such as wine? So I bought them some wine, then asked them to do the experiment whether the system can differentiate between different wine smells. So the when you open the wine bottle, you can feel some quite unique smell, and they're actually made of many different types of VOCs. So that mixture of VOC will make a unique scent from the wine. So this system actually is able to uh, train and able to generate this different spike signal by the combinatorial effect of multiple VOC molecules, which makes the scent. And then the system is able to tell the difference between different smells and type of wines also. So we call it so kind of artificial sommelier, which is actually, I think, too much of exaggeration, but we actually try to make this demonstration to make more fun. And now I'll talk about the ultra low power gas sensor in the range of 10 nanowatt to 100 microwatt per sensor. So so if I talked about the micro heater platform, so a lot of people actually have tried to make smaller and low power micro heater platform. One way is actually to make these micro cantilever structures, which has kind of freestanding structures to make the more efficient heating without losing much of heat loss to the substrate. And also, many people are working on nano heaters or self-heated sensors. They're quite powerful approach. However, their fabrication is more complex. And then cost of fabrication is much higher. And also, if you make this a tiny and highly localized heated region, you will think about the high thermomechanical stress because of localized temperature. So this will cause the mechanical and thermal damage to the sensors. So the reliability is a big issue. So because of that, quite a few people in the past decade have worked on the some alternative approach to activate the gas sensor through the photo activation, like by applying the lamp or LED, they could activate the metal oxide gas sensors. In our laboratory, we recently developed highly integrated and monolithic uh, sensor platform. Instead of using the external light source, we could integrate the light source with the gas sensor on the same device. So this is the micro LED, gallium nitride based UV micro LED. And then we've got some dielectric layer for the electrical insulation. And you can see the distance the sensor and between the sensor and the light source is only 1 micrometer. so that yeah, you have quite efficient transfer of the light energy directly from the micro LED to the gas sensor. And then the advantage of this is actually we can lower down the power consumption dramatically. And we can also make them in array platform. And the fabrication process is actually quite similar to conventional micro LED fabrication, but in addition, we've got some additional passivation layer with the interdigital electrode and sensor materials. And you can actually use various sensor materials, but here we use the glancing angle deposition using the RF sputtering. So by tilting the substrate of with the angle of 85-degree, we can actually use the shadow effect to fabricate this. I'll show you the image here. This nanocolumnar structures, even with the sputtering process. So that's the advantage of the glancing angle deposition to make a higher surface area for the reaction with the gases. So this is a fabrication result. We can make various sizes of the micro LED. And then use array of two different sensors. One is the indium oxide with the silver nanoparticle coating, and another is the same indium oxide with the gold nanoparticles. By the way, the silver or gold nanoparticle, they're activating the surface of the metal oxide by the surface plasma resonance effect, which makes the more active generation of the hot electrons on the surface of metal oxide. However, because they are using two different metals, they actually show quite different sense of responses. Then by analyzing this trended response of two different sensors and then training them using the CNN approach, we can do the classification and also the regression of the gas type and concentrations. And this is a result of the um, deep learning. So here you can see the confusion matrix. It shows a quite high classification accuracy of 99 above 99%, and also regression. The mean error, average error is lower than about 14% for various types of target gas molecules, such as ethanol, nitrogen dioxide, acetone, and methanol. And you can also do the real-time regression and classification of multiple gas species. And the biggest advantage of this one is, as I said, the power consumption. The power consumption as compared to the microheater platform, usually the commercial gas sensor using microheater platform is like 20 milliwatt, even higher. But our sensor actually is 100 times lower power consumption than the state-of-art MEMS-based microheater structure for the gas sensor. And also, the temperature for during the operation is actually almost close to the room temperature. We don't generate the heat by the micro LED, but we actually just activate the material with the light energy. But the temperature rise is actually lower than 5 degrees Celsius compared to the room temperature condition. And that is quite useful for the applications where we need to worry about, flammable or explosive gases like hydrogen or methane. Because by using the micro heater, they could be actually quite small ignition point even with the small microheater. But this micro LED actually, since it's operating at the room temperature condition, it doesn't work like an ignition point. So that's quite safe to use in that, hazardous and flammable situations. So because of that, we are collaborating with a lot of, domestic appliance companies to apply this sensor for their electronic appliance or mobile applications. We can activate the metal oxide material not by the steady state illumination, but also by its dynamic illumination. You can see this blinking light, and then more specifically, we can tune the time varying illumination intensity of this micro LED. Then what it does is actually it photo activates the metal oxide. This photon current will change by the varying illumination intensity, but their profile, the transient profile actually is dependent and determined by the type and concentration of the target gases in the surrounding. So by analyzing this transient shape, we can actually tell what type of gas and their concentration exist. A bit more specifically, we use this kind of transient response of the gas sensors, and then by looking at this transient response, this response um, you can see not only the time response, but we convert this to the frequency domain. Then this spectrogram actually can be used for the training. This spectrogram change actually is used for the CNN training of the gas sensor response. That this actually is able to give us the real-time classification of gas type and concentrations. You can see the configured matrix actually compared to the previous result, the classification accuracy is relatively lower. And also the mean absolute error is actually a bit higher. The point is that here, instead of using multiple gas sensor, we use only a single gas sensor. But by using this dynamic signal, we can actually make a classification and also regression quite accurately. And here I want to emphasize that using our technology, we are actually able to analyze not only a single gas, but also the mixture of multiple gases. You can see here we put our target gas, such as methanol and ethanol, and if both of them exist, you can actually tell both exist. And then also at the same time, we can get the concentration for individual target gases. And by changing this UV, this UV light source, we can change it to the blue LED. And the nice thing about blue LED is, especially on the gallium nitride platform, is it's got high external quantum efficiency. So it actually shows a more energy efficient activation of the metal oxide. So we can lower down the power consumption by almost about 1,000 times. So compared to the micro heater platform, we can actually lower down the power consumption even down to 100 nanowatt level, which we are quite excited about. I think my time is actually wrapping up, so I have to speed up a little bit. Just 1 second. Just give me 1 second. Okay. Um, And I'll talk very briefly about the ultra low power gas sensor, which is actually used instead of ultra low power, we can also make this self powered gas sensor platform. And a lot of people, especially in China, and also the group from the uh, Zhongli Wang group, people have developed tremendous work in the triboelectric nanogenerator or piezoelectric nanogenerator for the self-powered chemical sensor. Instead of using those mechanical energy harvesting, we also wanted to use some alternative approach, such as light energy, which are quite abundant in the ambient condition in the indoor or in the outdoor from the solar power. So here we had the solar cell as some kind of energy generating, but at the same time, the detection device and the light from the ambient environment or the or outdoor sun. The intermediate layer, we are using this light, the colorimetric structures. For example, this is the micro nano hierarchical structures using the micropost and the nanowires, and then coated with some colorimetric materials such as TMPD. When nitrogen dioxide is exposed, then the TMPD actually shows this transmittance change in the range of 450 to 650 nanometer range. And then if you use a proper combination of the organic photovoltaic cell, we can actually measure the change of the light transmission through this sensing layer quite sensitively by the measurement of the changing current from the solar cell. And then you can see by using the hierarchical structure using micro post and nano wires, we can actually dramatically increase the reaction area for the gas sensor. You can see a dramatic improvement of the gas sensor response. A little bit of modification, but with similar method. We use the current output from the solar cell, but here the sensing layer we use the fabric parastructure using the hydrogel. The chitosan is one type of hydrogel which shows the volumetric expansion by the relative humidity, and that when there is a thickness change, the peak wavelengths is actually changed, and then you can actually detect that by the solar cell output. And also we use this linear grating structure made of polymer nanoline structures, which is coated with the palladium thin film, asymmetrically deposited by glancing alkyl deposition. And when hydrogen gas comes in, you can see that the expansion of palladium to palladium hydride. Then it tried to expand, but because of this underlying polymer structures, it actually will be bent, and then will block the light, and which will be detected by the photovoltaic cell. And well, to be honest, actually, we are talking about cell-powered sensor, but it's not actually a cell-powered sensor system. Uh, you know, you actually need a quite sophisticated and big equipment to measure the change of current from the solar cell. So it's not truly self-powered system. To make it this self-powered system, we want to make this instrument for the measurement in a very tiny and low power. So I collaborated with my colleague at the EE department at KAIST. This ASIC chip is like ultra low power. It gets the power from the solar cell. At the same time, it is able to process all the data from this self-powered gas sensors. I think I'll use about 2 to 3 minutes to talk about a couple of examples that we have collaborated with some Korean companies. So we developed this low power gas sensor and apply them to some environmental monitoring system in the semiconductor industry. So in Samsung Electronics, actually talking about a few nanometer fabrication. And for that, the tiny amount of the gas uh, uh, emitted from the wafer substrate is actually quite critical for the next step that can cause the cross contamination. So this tiny ppb level or even ppt level concentration should be monitored. And then we actually develop some system that could be attached on the front opening unified port, which is a wafer sort of carrier between different processes, and this was able to do the real-time monitoring of the gas species. And this is the portable system that we have developed for their pilot test. And also in collaboration with the Hyundai Motor Company, we actually use our sensor, photoactivated gas sensor. Uh, the reason why we use the photoactivated gas sensor is that, this water hydrolysis, water electrolysis system. We're talking about hydrogen, high concentration hydrogen, which would be quite flammable. So we use this photoactivated gas sensor for the monitoring of the oxygen leakage into the humid hydrogen environment, uh, that could detect the this leakage in a very short amount of time. And lastly, we also use our sensor for the gas leakage point detection by installing only a few locations. Then by collecting the time response from a few number of the gas sensors, we can use the training data from the computer simulation, CFT simulation, to train the sensor, train the network, and then use that trained network to do the analysis about the experimental data from the only a limited number of gas sensors. And this could do actually the quite quick detection of the leakage point in some industrial sites. And that work was done in collaboration with Samsung Heavy Industry. So with that, I'd like to conclude my talk. I think I tried to keep the time, but I think I was a little bit behind my schedule. And also in the meeting, in the middle of my talk, actually, my wife actually ran the vacuum cleaner. Actually, I was quite embarrassed about. I just kept telling her and just somehow ignored. So I think in the middle of my talk, you could have listened to some noises. I was a bit nervous about that. So sorry about that. Anyways, let me conclude my talk. Um, in our group, we actually are doing our best to minimize the tensor structures. Not only minimize, but also try to develop some new operation method of this miniaturized gas sensor. Not only the micro heater, but also the micro LED platform to lower down the power consumption, to make it more miniaturized, but also still more powerful for more accurate gas sensing for truly powerful electronic node systems. Right. So I'd like to acknowledge my students. I'm always going around and talk about my stuff, but actually the students are always doing the work, especially my graduate student who graduated and are working at Samsung Electronic, Mr. Incheol Jo and Mr. Hichul Lee and Minggu Kang. They are somehow here together, but they actually are gas sensor, the main players of the gas sensor group. So I really appreciate their hard work and effort, and also my funding sources and collaborators, and also really appreciate your kind attention and understanding. All right. Thank you very much.
Okay, thank you
By the
very
way, did you
much,
hear some
Professor
noise?
Ing. No, we haven't heard anything.
Oh,
So if you didn't tell us, I think we would know. We would not know at all.
okay. Okay.
So you just
Okay.
revealed your secrets. Okay, thank you so much for sharing the extensive research of in your research team, and I'm quite impressed because I know that there are other research topics going on in your lab, and then this is just the gas sensor part, but still it's a lot, so it's amazing.
Thank you.
So thank you very much, and if you can stop sharing your screen, then we will start
Sure.
our next. Okay. So now it's time before we ask questions to Professor Inkyu Park. So this is the time to introduce our amazing members. First, let me introduce Dr. Stella Baihos. I hope that I pronounced correctly, Stella. So
Yeah,
from
that's
the guest.
perfect.
Oh, okay, thank you. From the guest sensors group at the Instituto, uh, the Microelectrónica de Barcelona. Is it okay? Okay. So this it gives me some challenging time. So Dr. Stella Vios is currently a tenured researcher and coordinator of the gas sensors group, as I said, and she has held so much competitive fellowships, including Marie Curie, and now she's currently leading two European projects and then also the three national projects funded by the National Research Agency Spain. And also she has a contract with end user industry partners as well. So from her bio, the one sentence drew my attention a lot. All her activities allowed her to approach younger researchers and the non-specialized public via all these activities, particularly to young women audiences. So you might want to share your own wisdom today a little bit. And next, I'm going to introduce Professor Shu Hee Sun. I practice, sorry. So, from the Institute of Functional Nano and Soft Materials. And he got his bachelor's and master's degree in chemistry from Tsinghua University. And then he got his PhD from the City University of Hong Kong. And he used to work at NASA, and now he's a professor at Suzhou University from since 2009. And then he has a number of papers, publications, and or other achievements. And let me introduce our next panelist, Professor Zi Xiong from Shanghai Tech Universities. Today, I'm having some trouble here in pronouncing all these names. Sorry about that. So, Professor Xiong is an assistant professor at Shanghai Tech University, and he received his PhD degree from the University of Hong Kong in 2017. And he has published so many papers, including Nature Biomedical Engineering and Nature Materials and Science Advances and Advanced Materials and ACS Nano and etc. So he got so numerous awards and then or other patents and all those things. And last but not least, let me introduce Professor Fei Wang here. Professor Wei Wang received his bachelor's from the University of Science and Technology of China in 2003, and he got his PhD degree in microelectronics from the Shanghai Institute of Microsystem and Information Technology, Chinese Academy of Science in 2018. And he used to be he worked as a postdoc and also the assistant professor in Denmark, and he joined the Southern University of Science and Technology and now he's a full professor and the vice dean of School of Microelectronics. Welcome everybody on board, and then we will start our panel discussion here. So first, what we can do is we can ask so many questions to Professor Inkyu Park about his research. So you know the rule, right? Okay, so who wants to go first? Stella, would you want to go?
Okay, thank you.
Yes.
Thank you, Miso, for the introduction. And thank you, Haisha-san, for the invitation. I'm happy to be here in this discussion. I have to say also thanks, Professor Park, for the presentation. It was a very nice journey through the state of the art and also through your own research. And well, I have a couple of questions that I would like to, that probably I didn't catch very well from your presentation, and maybe you can explain a bit more. As you were explaining about the integration of materials directly on monolithic chips by hydrothermal synthesis, I was wondering how you avoid the contamination of these materials in a matrix of different materials, right? You're explaining that you are using a microfluidic system to avoid that contamination. But I was wondering what, when you come to the practice with this type of chip, what do you do later with this microfluidic system? Do you use the same microfluidic system during the analysis of gases, or do you remove it somehow, this system? How does it work? Because for the hydrothermal synthesis, I understand you will need some surfactants or other materials that can also contamine the channels of the microfluidic system, right? How does it work that?
Okay, very good question and very important question. And well, so I demonstrated one example of parallel synthesis of multiple nanomaterials by microfluidic supply of the precursors. That's only one example. Other things actually we actually have done without the microfluidic channel. We actually use some open sort of a droplet kind of precursor on in an open space. And back to the microfluidic channel. After we do the chemical the hydrothermal synthesis in the microfluidic channel, we use various fresh water to sort of refresh or rinse whatever kind of remaining uh, precursors on that are still remaining on the synthesized nanostructures. So the contamination actually issue is not actually was not a problem. Even inside the microfluidic channel with the laminar flow, there will be a very tiny amount of the diffusion occurring between different sites of the precursors. But by according to the calculation and also according to the EDS analysis of the materials after the synthesis, there was no cross contamination between different nanomaterials synthesized in the microfluidic channel. But plus, after that, we also do additional rinsing through the microfluidic channel. And outside microchannel, in the open space, what we do is actually we make a droplet of the precursor, and then we apply electrical voltage, and we generate the localized hydrothermal synthesis. Even for that case, after the synthesis, we do various rinsing processes to avoid any kind of cross-contamination issue.
Okay, thank you very much for the explanation. Misa, should I continue with another question or do you want to pass to another panel?
It's okay for you to ask two questions.
Okay, perfect. Professor Park, I was thinking in relation to the selectivity, I would like to know your opinion regarding the use of systems, for example, like sensors activated by light. Is the light going to act somehow to improve, let's say, the selectivity of the system? How do you think? Do you think that the material is still important, the gas-sensitive material, for this adjustment of selectivity? What is your opinion regarding to this type of systems activated by light? Can they have some advantages for selectivity?
Yeah, that's also a very good question. Gas sensor, especially the semiconductor metal oxide gas sensor, they react with a lot of different gases so randomly. So they have a very poor selectivity. So selectivity is a really big issue of the semiconductor metal oxide gas sensor. Uh, but people use, different catalysts that can be more sensitive to a particular type of target gases. Uh, but just by heating, also we depending on the operation temperature, uh, the metal oxide may have different selectivity to different target gases. And also according to the light intensity, they also may change their selectivity to different type of target gases. So we can tune the intensity of the light to tune the selectivity, but actually that does not give a full answer. What we do is actually is we make an array of at least a couple of sensors, and then we shine the light, and then we obtain the sensor signal, and we try to analyze the sensor signal, not only the steady state sensor signal, but also transient sensor signal. And then we just try to use the machine learning to compensate for the poor selectivity of metal oxide gas sensor. Plus, I briefly showed you our time varying illumination, which actually gives, the changing uh, photocurrent of the semiconductor metal oxide. And that dynamic sensor response actually did help a lot on improving the selectivity between different gases because we can actually collect more rich information from the dynamic signals of the gas sensor, which is realized by the time varying activation of the time varying light illumination control of the light. So I hope this gave you some answer to your question.
Yes, thank you very much. Yeah, as you say, indeed, the selectivity is a question of several parameters, indeed, that need to be optimized in order to
Yes.
achieve a better sensitivity or selectivity, sorry. Okay,
Absolutely. Yeah. Thank you.
Okay, thank you, Stella. So you might want to hear any feedback or questions from Professor Fei Wang.
Hello, can you hear me?
Yes.
Yeah.
Yeah. Hi, Inkyu. It's very nice to listen to your talk once again. And every time I learn something new. It's a very wonderful talk. And I think there are plenty of applications we can try for the smaller and lower power consumption of the MEMS gas sensors. And I noticed that you have set up a lot of collaborations with Korean companies like Samsung and other companies. So I'm wondering, for those kind of applications, are you using the state of the art of your new MEMS gas sensors, or you are working with mature technologies for the application? I mean, for companies, they would be hesitate for fresh new technology, which is not 100% mature, right? So I'm wondering, what's uh, the most challenge, the largest challenge when you're trying to collaborate or put application of those kind of MEMS sensors for the company applications?
Okay.
Yeah.
Yeah. That's an excellent question. And so when I collaborate with the companies, um, those companies actually they want state-of-the-art, newly developed sensors, but also they want the real product and real practical deployment of those technology in 2 years or 3 years maximum. That's a dilemma.
Yeah.
And also they want like really high reliability.
Yes.
But in many industrial sites, actually, a lot of mechanical vibration, shock, very harsh conditions. So that kind of practical deployment and in with a high reliability is not quite easy. Um, in case of the first example, the and my collaboration with Samsung Electronics,
Mm-hmm.
they actually wanted to develop some very compact module on the vapor carrier called the FOOP, which is actually traveling inside the semiconductor manufacturing sites. Then
Mm.
it's not quite easy to supply a continuous power to those uh, gas sensing unit. So the module actually should be quite energy efficient. In that case, we could not, and also the original hoop size is so compact, so adding additional size was quite limited. So we had to develop very tiny module plus sensor array, and also that should consume a very low power. So we actually applied our uh, low power microheater based multiplex gas sensor array. Then they actually somehow sacrificed in terms of reliability. They wanted to just sort of find out some proof of concept in their new manufacturing line. Then we actually collaborated together. And then we used our newly developed low power gas sensor. Then we developed about 40 to 5 module for the pilot test. And then we're still, doing our collaboration and discussion together whether we can actually prove the high reliability for their real applications. Um, Another example with Samsung Heavy Industry, they actually wanted to apply that to their manufacturing site or to their engine room, like of a big ship. In that
Uh-huh.
case, the reliability would be a big issue because it has a lot of mechanical shock or vibration.
Yeah.
For that case, we went in parallel. One, we use a single sensor unit. We use a commercial sensor. Also, we use our developed sensor together to collect a signal. And we compare like their pros and cons in the same project development.
Thank you.
Okay. I'm not sure if I gave you a full answer to your question.
Yeah. I think it's always very challenging to put it to practical application because
Exactly.
the environment is totally different from our lab, right? Yeah.
Absolutely.
May I ask another question? Yeah. Um, Actually, I think for the gas sensing, machine learning technology is a very, very important tool right now. So you need to do some data training, then you can use this as a very smart sensor to predict the sensing performance, right? And it might be very useful to improve the selectivity. But I'm wondering that when you do the data training for the sensors, um, have you considered some practical issues in the application scenarios like humidity effect and some other heating or other issues, like you mentioned, a hazardous environment. Because for typically, if you do the data training in a perfect lab, then do the prediction in a perfect lab, you can easily get a good prediction, right? So I think it's very interesting for your one application to recognize the different type of wines. I think humidity might affect the machine learning. So I'm wondering, have you considered any other parameters in addition to the gas itself during the data training?
Absolutely, that's a quite critically important point. And then we also uh, recognize that's a quite important issue. So when we do the training, we control the humidity and temperature in different values. So we actually do the data collection in different levels, but we cannot do all of them. But we use a few representative conditions, dry, perfectly dry, 20% relative humidity, 40, 60, and 80. And then we cannot do every single percent, but through those discrete number of conditions, and then by those training data, what we could observe was only with the limited amount of environment conditions, such as the humidity and temperature,
Mm-hmm.
it could do pretty good interpolation by the machine learning. So,
Yeah,
so it could estimate some intermediate relative humidity and temperature levels too. And of course, that actually requires a lot of work.
yeah,
Practically, the gas sensors actually compared to the photo sensor or physical sensor, takes much, much longer time to obtain the data.
yeah,
So it
indeed.
actually consumes a lot of effort and time. So we try to automate all of the experiment procedure by doing some lab recording to do some multiple data collection without intervention by the human operator. Uh, but I think, uh, uh, to be honest, that still is quite limited. So, but as you know, the gas sensor lacks some kind of physical modeling. But if we
Mm-hmm.
can come up with some kind of better physical modeling or mathematical modeling, then we can probably, instead of running all the experiment by experiment, we can probably do some simulation that can fill in some gaps that could help us to provide much more rich data for the machine learning. And hopefully through that, we could probably improve our machine learning based electronic node system, hopefully.
Thank you. Thank you very much.
Okay, considering the time allowed for us, I think it would be great if we can move to Professor Sun.
Hi, yeah. Thank you for Mr. Kim, and also very nice talk from Professor Park. Actually, I commercialized the MEMS-based semiconductor gas sensor 10 years ago. I have a company work for that. Actually, I know the pain spot of the reliability, stability of these gas sensors, especially for this MEMS-based gas sensor, because you need to control the quality of the heater, also the how to put the material, sensitive material on the heaters. Yeah. Actually, we also do the AR. Actually, for AR, it's a eNodes. The big challenge actually is the uniformity of the sensors, because you cannot train the individual every sensors for the database, right? You have to keep the other uniformity of this all gas sensor especially for mass production. So how do you to comment on that of this question, the big challenge of the uniformity especially for the mass production, for the future use of the eNodes?
That's absolutely wonderful and very important question. The uniformity is really important, especially for the machine learning based eNode system, because as you said, if we train with one sensor, if another sensor is totally different, then the machine learning actually is basically a garbage. So the uniformity should be definitely achieved by some good manufacturing method, and we have also put a lot of effort to solve that problem. What we found was instead of chemical synthesis or hydrothermal synthesis, that could be scientifically interesting, but to be honest, in terms of commercial approach, uh, I believe the top-down fabrication approach should be much more practical. So I showed you one example using the glancing angle deposition for, deposition of nano like sensing material. By tilting the angle and using the sputtering approach, we can make a quite high surface area nanopore structures, but with much higher uniformity between the devices. So, for example, if you use the inkjet printing or electrohydrodynamic printing or pre-synthesized nanomaterials by those processes, we could see a quite large variation of base resistance and also the response, which is the relative change of resistance by large and plus minus 30 to 50%. But if you use the glance angle deposition, we could actually suppress it down to plus minus 10%, which is actually much better uniformity. And with that variation, what we have found was in the machine learning process, we could actually um, intentionally provide the data from big variance, but we're talking about plus minus 10% at most. Then this actually machine learning could give some good tolerance for some error. Then that actually, even with some variance, that the training with tolerance, some data with error, it actually could provide quite robust estimation in terms of the classification and also the regression. So yeah, I'm not sure if I gave you some full question answer to your question, but maybe you should first try to make manufacturing more repeatable by in my preference, by top-down verification.
Yeah.
And then second, when you do the machine learning, try to put the data from intentionally different set of sensors, which can give us more robust uh, machine learning result.
Yeah, I totally agree with you about this top-down process. Yeah, we try to do that in our company. We already sell the millions of the single gas sensor, MEMS gas sensor already into the market. Yeah, another question is about, you talk about the mechanism of the MOS sensor, right? For needed in the oxygen environment, right? Some critical application, for example, now in the this lithium battery cell, they want to put the gas sensor into that. It's actually it's non-oxygen the environment to detect the thermal runaway process, right? So how to comment on that in the non-oxygen environment, the MOS gas sensor, how to work on that? Is any the possibility to in the material aspect to develop this kind of the non-oxygen the environment gas sensor based on the MOS?
So you are talking about the thermal runaway monitoring in the lithium-ion battery?
That's is one the practical application. See, it's that's because in the non-oxygen environment, right?
That's as far as I know, especially particularly in the lithium-ion thermal runaway example, I think there will be ambient air molecules which has the oxygen. So in
No,
that case, I think
no, they want to put the gas sensor inside the cell, the battery cell.
inside the cell.
Yeah.
If you have a perfect sort of packaging
Right,
with
right.
no.
Actually, yeah, another because I was the work at the NASA Ames. They put in the gas sensor in the space. The space with no oxygen, right? So how it's the same the environment. How to develop this gas sensor is a non-oxygen environment based on this metal oxide or semiconductor.
Yes, that's something that I didn't think very carefully before. But as far as I know, one approach could be to generate some hydroxyl group at the surface by some surface like oxygen plasma treatment or etc. Then those hydroxyl groups actually can capture the reducing gases. Then instead of having the oxygen ions, we can use the hydroxyl group to react with the reducing gases, probably.
Yeah, probably, yeah. Okay, yeah, I know, because another probably they have oxygen vacancy, right? They can also keep work on that. Yeah, actually, it's very interesting topic. People ask me how in the non-oxygen environment, how to work with that.
Yes, that's actually a very good comment, and I'll think about that. Thank you very much.
Okay, I think I need to really interrupt here. Sorry about that, because we only have a few more minutes. So can you move on to Professor Xiu so that he can share his comment or question for Professor Park?
Yeah, thanks, Ms. Kim, and thanks for Prof. Park. I think it's amazing talk today. I'm not a professional in the gas sensing field, but I'm still very impressed by your presentation and research. I actually, I'm kind of like the end user, because we fabricate a lot of system to sense different like wearable or implantable in different scenarios. So specifically for your case, I'm wondering, actually follow the previous question raised by the Prof. Sam, because I'm not familiar with the machine learning. So is there any possibility that you can just use the trained model, for example, and just just transfer to another device? Because or how many devices you needed to train a good model for using? For example, you can use only one device, or you need like many devices to complete your training. I'm just curious about that. Yeah.
Okay, that's also quite important and critical question. So for the machine learning to be powerful, we need more data. The more data, the better. However, we cannot actually use hundreds or thousands or 10,000 sensors, especially for the gas sensors, because the instrumentation of gas sensing experiment is quite bulky, and also it takes a long time to obtain the data. So in our case, we use at least 10 to 20 different sensors, and then per each sensor, we try to run at least 20 to 30 different cycles of the same experiment. So by that, we could obtain enough amount of data for the machine learning. The machine learning, if you do the image analysis or voice recognition, they need much larger amount of data. But the gas sense actually, by their nature, we don't need that much amount of data. But instead, as I said, about several tens of sensors for several tens of cycles actually are, yes, quite sufficient for the training of the gas sensors for the electron systems.
I see. It's great. I think it's once you have, I think from the previous discussion, I know that once you have one model just to train, and then you can just translate that into some other sensor and use that model to explain what you get, right? I think that's a very usable approach. And so maybe as an advertisement for your future student, I'm asking for what kind of capability or kind of ability you are looking for the coming, like a graduate student or postdoc working in your lab, right? What kind of criteria or most important feature you are looking for? Yeah.
Yeah, thank you very much for asking that question on behalf of me. So I really also look for excellent students from like anywhere in the world, including Korea, China, or any place. And because our lab belongs to the Department of Mechanical Engineering. Well, people might think that we do a lot of mechanical engineering related work, but we actually do some mechanical design for the sensor, but we use a lot of interdisciplinary research. So we do quite close collaboration with electrical engineers, material scientists, chemical engineers, and also physicists. So I want the student with open mind, and also quick and easy learning, and also the passion for learning new things, and endless effort, which means quite difficult. But this kind of experiment actually requires a lot of time, effort, and perseverance. And I'm an experimentalist, which means I do a lot of. Some people say it's kind of labor-intensive work, but at the same time, we should be very smart in doing the experiment. So, being smart, but also working hard is a very important virtue for the students that I'm seeking for.
Yeah, thanks for your answers. Yeah.
Very much.
Thank you. Yeah, thank you so much, everybody, for sharing all those like invaluable questions. And then, Professor Park, thank you so much for your satisfactory answers for us. So that was
I can get a
our
certificate, right?
contract. Yeah, you will get the certificate. And actually, there was a quick one question from the audience virtually. So why don't we make the sensor more sensitive rather than using complicated algorithms? So
Ah,
using rather than
yeah,
using
yes.
those AIs.
Good question.
Yeah, very good
Of course, you
question.
can. So the material scientists actually they try to design the material to be much more stable, much more selective, and much more sensitive. That's one effort. I think that the effort is very important, but that actually cannot solve all the problems by itself. Because even for those excellent materials, they may still have high influence from the varying humidity conditions, temperatures, or they can also be affected by the interferent gases. So we need some assistive technology. Some people do develop some filters for filtration of some interfering factors. But another very important approach is, as we do, we use some machine learning, and not only machine learning, but by playing with some operation method like we do, we try to have some time varying operation. Then we can collect more rich information from the sensor. We use the same sensor, but by tuning how we operate them, we collect more data. And then by analyzing with the machine learning, even with the same material, with the same device, we can actually have much more like rich information for improving the performance in terms of sensitivity, response speed, selectivity, and etc. So that's a good question, but in summary, machine learning definitely would be also a crucial part in improving the sensor performance.
Thank you very much. I don't know who the person is who asked the question, but out there, I hope he or she would be very satisfied with the answer. Okay, thank you so much, everybody, for being with us today and then sharing all your moments here. And then let me give Professor Park. Okay. Let me deliver this nice prestigious virtual certificate to Professor Inkyu Park today. And then we are so proud of you to be a member of iCANX here. And thank you so much for sharing your great research stories with us today. Thank you. And then you got it.
Thank you very much. Thank you very much.
Okay, thank you very much. And then that would be it. And then let me just make a great announcement about iCANX Davos Summit that will be held and which will be held in Davos, Switzerland this July. So try to search what iCANX Davos Summit is. That would be our first Davos Summit. And not only the science technology, we are going to have all those people and experts about investments and management and even the entrepreneurship. And then there will be amazing gala dinner and then party as well. So just join us next in July, so in Switzerland. And next week we are gonna have Professor Lee Kyung Mai from Wuhan University of Technology. So join us next week again, depending on where you are, just from the morning or from evening, anywhere. And that'll be it. And thank you so much for being with us today again. Thank you very much. And depending on where you are, have a good night or have a great day. Bye-bye.
Hello, ladies and gentlemen, my dear friends. Welcome to iCANX Davos Summit. So this year we're going to have this big event in Davos, Switzerland. We have 6 topics: innovation, science, technology, investment, management, and entrepreneurship. Short for It's Time. So it's time for us to go together. It's time for us to all these inspiring talks for the future. We'll have Nobel laureate firms. We'll have president of academic firms. We'll have president of university firms. All these big names will be here to talk about the future, what's going on for the future. We also invited all these world leaders, scientists, investment management to go together to talk about, what technology and science going to be for the future. And we're going to listen to many sharp talks. All these great figures was from each field. They will share the sharp ideas, the latest results. So it's not only a platform for all these big names, for these shining stars. We also invite you to share your stories. So it's time for you to deliver a talk here. So you are welcome to submit your materials online. So we have many sub-sessions, parallel sessions. You are welcome to submit your materials, and we're going to pick up someone to share that. And it's our time also invite you to be superstars on the stage. If you are college students, welcome to apply for Innovation Award. If you are young scientists, welcome to apply Young Scientist Award. If you already have your startup, welcome to our Startup Award. All these applications is due April 1st, so you have about months to submit it. And it's time for us to go together. We have all these people here who want to work together with you. So we from different continentals, different countries, different areas. So welcome to join us, and it's our time to go to Davos. Now the pre-registration is open now. You are welcome to submit online and go summit together.
在持续发展的社会中，电子元器件需要应对日益复杂化的要求和越来越高的期待。技术革新浪潮汹涌而至，对其高性能的需求、无限小型化的追求，成为行业发展的必然趋势。多层陶瓷电容器、电感器、高可靠性元器件、太阳诱电支撑其全流程的先进技术，提供给用户全方位的服务。为了科技的发展，我们一代代太阳诱电人肩负使命，激情拼搏，以极致的匠心独运，呈现出史诗级作品。研发历程感动了无数电子工程师。太阳诱电将深深吸引全世界的目光。
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 iCANX 达沃斯科学峰会。那今年是第一次 iCANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，